And Dixie, whenever you're ready, you can start. Go ahead.
All right, thank you, Principal. Thank you everyone for joining us. Today's seminar is on heterogeneous stress relaxation in thin films, whiskers, hillocks, and beyonds. And it's a great privilege to introduce our speaker, Dr. Carol Handwerker, the Reinhard Schumann Junior Professor of Materials Engineering and the Professor of Environmental and Ecological Engineering. So as you can see, Professor Handwerker got her BA in Art History from Wellesley College in 73, a BS in Material Science from MIT in 78, a Master's in Ceramics and a Doctorate of Science in Ceramics, both from MIT in 78 and 83. Prior to Purdue, Professor Handwerker was at NIST for 21 years, serving as the co-lead for advanced packaging as well as the chief of the NIST metallurgy division for the last 9 years at NIST. Professor Handwerker currently leads a $40 million 5-year DoD program in facilitating the transition to lead-free electronics in defense systems, and is also the co-PI of SCALE, a major DoD project on workforce development for advanced microelectronics. She was the director of the Purdue Tuskegee NSF Integrative Education and Research Trainingship Institute on Global Sustainable Electronics, supporting 28 two-year fellowships from 2012 to 2019, served as a member of the INEMI Environmental Leadership Steering Committee, along with Intel, Dell, and Lenovo, and also co-led the INEMI project on value recovery and end-of-life electronics with Seagate, Google, Microsoft, Cisco as team members. She was the co-lead of the lead-free alloy selection in the INEMI lead-free solder project that selected and implemented SAC 305 as the global replacement for lead for tin lead in consumer electronics. She is a fellow of the American Association of Advancement of Science, ASM International, the American Ceramics Society, the Materials Research Society, and TMS, and received the TMS Leadership Award, the TMS Applications to Practice Award, the TMS FMD John Bardeen Award, the Federal Laboratory Consortium Award for Excellence in Technology Transfer, and the Department of Commerce Gold Medal for her leadership in lead-free electronics. Her current research interests include developing innovative interconnect technologies for next-generation microelectronics and advanced packaging and sustainable materials for thin-film solar cells, improving the reliability of lead-free solder interconnects, particularly for high-performance military and aerospace electronic systems, integrating sustainability in the design of new electronic materials, processes, and products, identifying and implementing strategies to move R&D into manufacturing and commercialization, using road mapping, techno-economic analysis, and the formation of self-assembling socio-economic systems, and controlling interface properties to design microstructure and polycrystalline materials and thin films. And with that, I would like to hand it over to Professor Handwerker for her seminar.
Wonderful, Aditya. Thank you very much. That was quite a long introduction, and I can't tell you how pleased I am to be here and to talk with you and the students there. You could see I was a student at MIT, and actually when I was a student there at Worcester Polytechnic Institute, they were doing a lot of really incredible work in developing new processes for metals, metallurgy, ceramics. And some of the most exciting field trips I ever went to were in conjunction with people at Worcester Polytechnic Institute. So this one memorable one in particular, forging humongous titanium castings was just, it was life-changing to me. I also want to tell you how much I appreciate the work, all the work that you're doing there in recycling recovery, using thermodynamics for good in the world and kinetics for good in the world. Professor Powell and I have known each other for many years, and so I'm very pleased to be here to interact with you, you and all of you, which you're probably many of you his students as well. So thanks so much. Yeah, he said, thanks for not giving the number of years we've known each other. Quite a few. Since he was a child. I wasn't a child then. So you can tell from my bio, I like to be busy. I'm a very mission-oriented kind of person. And so almost everything I do, in the interactions that I have, I try to figure out whether I can make a difference. And I particularly like filling the gaps in knowledge, or, providing some sort of key insight or key contribution that makes everybody else's work really have higher impact. So that's why I've done all this work in lead-free solders. And so what I'm going to tell you about today, and now I'm going to share my screen, is about a particular problem in tin whisker formation. Hold on just a minute, please. And you may never have heard of tin whiskers before. So after this presentation, hopefully you will know a lot more about these. So one of the things you may not know, so this is heterogeneous stress relaxation in tin thin films, whiskers, hillocks, and beyond. And I think you probably could surmise from the introduction too, I like to work with a lot of people. I like to bring groups together to solve problems. And so John Blundell and I have closely collaborated in this. We were all the way back from we were graduate students together at MIT. And then people at Germany, Karlsruhe Institute of Technology, the Max Planck Institute for Forschung in Düsseldorf, additional people still collaborating NIST in Marseille. So by seeing what was needed for the technologies and needed to understand how stress relaxation work, this is how we've assembled this team over the years, and it's been great fun. So I like particularly working on problems where there is that something different happens kinetically or over time. And so what we had been moving toward, like in this case, this is grain growth. And I'm going to refer to the top right, let me go to get a pointer coming. So it was the effect of chemical inhomogeneities on grain growth and microstructure in aluminum oxide. So this is a paper from a very long time ago. And so in grain growth, and you've probably been given lectures about this, about grain growth, you start for ceramics with small particles, and they sinter together, and the grain boundaries form. That's what you're seeing here on the top surface. The grain boundaries form. They sinter to high density. So then the pores between them are eliminated by diffusion. So I became fascinated by the problem of something called abnormal grain growth. And that is the microstructures are evolving in the ways on the top right-hand side, but then all of a sudden, something changes in the microstructure. Something has gone out of local equilibrium such that a few grains begin to grow at the expense of all the others. So the driving forces here have changed. And so these can be one grain out of, 10,000, 100,000 grains. So I've been working on this for these kinds of problems my whole life. So not just the average behavior, but also these very unstable situations where something else happened. So this is a tin thin film, analogous to what you just saw for the polycrystalline material for the ceramic, this is the top surface of a tin thin film. And so you can see individual grains and grain boundaries and surfaces are not flat. And, and so when we put these films under stress, something unusual happens. And so remember the size scale, that's 50 micrometers. So here is a plot of, this is from the work of Chasen et al. And so you take the film. Now it's on a silicon substrate. So the thermal expansion of silicon is different from tin. It's different by an order of magnitude. So when we put the we thermally cycle this material. So we have a tin thin film with a thermal expansion coefficient of 23 times 10 to the minus 6 per degree centigrade. And it's on a silicon substrate, which is about an order of magnitude different. It puts and you heat it up, it puts the tin film under compressive stress. So this is a plot that shows stress as a function of temperature. And this has been heated up at a uniform rate. So the temperature increases. This is compressive negative. So the stress begins to increase. And at some point, the stress begins to relax. This is a thinner film. We're not going to go into the thickness effects today, but the thin film, it relaxes the stress. And the way it relaxes the stress is by forming tin whiskers. So these are individual grains in diameter, and they can grow to millimeters, multiple millimeters in length. This is a set of connectors. So these are probably, I'd say, 5 or 6 millimeters apart. So these are single crystals that form from the film, and these are forming because they relax the compressive stress in the film. So it can be typically one whisker out of 1,000 to 20,000 grains. So again, this is a relatively rare phenomenon. And so I've spent quite a few years trying to understand what made those particular grains form whiskers. So here's a scenario. This is the tin film in this case, it's a copper substrate. And at room temperature, the tin and the intermetallic, the tin and the copper react to form an intermetallic. So remember that at tin at room temperature is about 60% of the melting point. So so there's plenty of diffusion that happens, and so these intermetallics grow. So what happens in this particular situation is when the intermetallics grow, they create a compressive stress in the film. So you don't even have to have a mismatch in the thermal expansion coefficient. The formation of this intermetallic leads to a compressive stress. And so if you see here, this is the way that we understand this. This is a schematic of a single columnar grain. And this is the film thickness, and they're essentially columnar grains. So these would be the grain boundaries. This is the substrate or the interface with the intermetallic. This is the free surface. So if you remember from some of your classes, that creep of a single grain under biaxial compression. So here's the stresses here. What happens is you end up with a stress gradient between the compressive grain boundaries and the free surfaces. So you get net motion of atoms from the boundary to the free surfaces. And so that's called if it's grain boundary diffusion control, Coble creep. And if it's a lattice diffusion control, it's Navarro-Herring creep. So that's a way that all of the grains in the whole structure could relax. However, in the tin situation, tin forms a very strong oxide on the free surface, and it makes this be a poor sink for atoms. So it suppresses it suppresses cobalt and Nabarro-Herring creep. So now you have a film, and you have lots of grains being stressed at 60% of the melting point. And the stress, how is the stress relaxation going to take place? Well, the way it takes place is that there are some particular grains in the structure, we'll get to exactly why and how, that can become a longer range sink for atoms. So diffusion happens over, not just in a single grain, but over multiple grains. And there's growth of the whiskers. So there's the substrate, and the oxide suppresses diffusional creep. So this is a typical microstructure. This is a whisker coming out at you. It's it's on the order of probably 30 mic. In this particular one, because this is coming out at you, you're seeing more like the projection. So this is maybe 30 to 50 microns in length. This is the structure of where the grain boundary is in the film. This was the original free surface, the top surface of the grain, and you can see the oxide has ripped here. This was the oxide. This was the original grain, and the whisker formed. It forms by growth from the bottom. So diffusion from multiple grains away from this is happening to relax the stress in the film by the formation of the formation of the whisker. So think about this as an extrusion, almost like an extrusion situation. You have accretion of atoms at the bottom, and it pushes it up, and so this grain has this particular configuration. This is a bib cross section. The spots here are actually an artifact of the fibbing, and it's some more general intermetallic. You can see the intermetallic compound forming at the interfaces, and this is the shape of the grain that has formed a whisker. So this is we call these a shallow grain. Most of the grains in the film are columnar grains. The shallow grain has a particular driving force for migration, for atoms to migrate there. So this was the cut through this particular grain, and this was the fib cross section. So one of the things that I really was taken by in this paper it was a review paper, was the idea that there's certain pattern formation for stress relaxation in polycrystalline films. That during deformation, defects in crystals tend to self-organize into patterns, which often reveal hierarchical structure. In our case of tin whiskers and some other things that you'll see there, other stress relaxation, they actually have signatures that can be used to identify them. So there are different types of lattice defects reveal in part different deformation-induced pattern characteristics, which often change in character and size scale as deformation proceeds. So there are many different things that happen, and they happen over time. So here's a picture of one tin whisker. And one of the things that's important here, and I have to tell you, this is my favorite tin whisker of all time. This is the original surface of the film. And so think about this is sort of the geologic time. This is how it grew out. So if you looked at it over time, each of these layers you would see happening as a function of time, and there's actually no diffusion, very little diffusion that happens in the whiskers themselves. So this actually memorializes, it retains all of the structure and processes that happen. So this grain was originally flat on the surface. It actually showed whisker formation, but only in part of the grain. So it tilts up. The grain boundary also migrated out. Then it migrates in, and then it migrated out. And there were changes that were happening in the grain boundaries, in the films, the underlying film, that led to these changes. And the bottom, this is a thermally cycled film where you can see there are a lot of changes that happen over time and we'll get to some of those later. But all of these are responding to the local stresses, how they change, and which deformation behavior actually begin to be dominating. So in our case, we have whisker formation, cracking, grain boundary sliding, grain boundary migration, grain boundary rotation. And so I'm going to try to hit some of the high points in the talk today. So again, this is my favorite whisker. And so here I've broken it down so you can see what the different steps were. So this was the first step in, it was a film from the free surface looking like any other film, other grain in the film. The grain boundary migrated out as it also accreted. So you can see that relative to the orientation here, this is tilted upward. So it migrated out, tilted upward, but not over on this side. It migrated back. So that's why it's undercut here. It migrated to this point, and then it began to migrate out. And then at some point, at about this position number 5, then the whisker uniformly grows from the film. And what that means is all of the grain boundaries that are present in here, all the underlying grain boundaries are all accreting atoms. The atoms are diffusing there, and then they're pushing up the whisker uniformly. So you can see what the underlying grain boundaries are. These are grain boundary grooves here. So this is the whisker. This defines where the grain boundaries are in the film for the whisker grain. And here, these are the grain boundaries of the film, the grains that are surrounding it. So this, again, is a shallow grain, and we'll get to some of those features in a minute. Now, I took a lot of inspiration in this paper by Trinks and Volkert. I had been working on this area for quite a long time, but they have done what I think is the definitive work in trying to break down what the different kinds of deformation mechanisms are operating. So what they did was they have a thin film, and as a function of the strain amplitude. So what they actually can do here is that they put a thin film on a cantilever, and they vibrate the cantilever, and there is a strain gradient along the cantilever. So this is along the length of the cantilever. So it's a vibrating cantilever, and it actually this is where the stresses are highest here and the lowest here. And with the cantilever, the stresses are highest at the hinge. So we have a strain amplitude. The strain's highest at the hinge, and then the stress is created there because there are strains as the film is bent. So what they saw in this particular case, they could see 5 different signatures on the free surface that show what the stress is being relaxed by different kinds of phenomena. And I won't go into all of these. They'll come up later as we discuss it. The other thing that's really interesting here is they did experiments as a function of film thickness. They did so here as a function of film thickness. They could see what the different distributions of damage were by different with different mechanisms as a function of film thickness. So this really opens up a wide range of experiments that one can do. So taking inspiration from this, the last set of experiments I'll show you were ones that we did on vibrating cantilevers for tin. So these are some of the key ideas. That almost every thin film, at least metal thin film, that stress relaxation is heterogeneous. It depends on the material. It depends on the microstructure, the crystallographic texture, the composition of the film, how anisotropic it is. And what the base microstructure is, it depends on what the stress state is, the strain rates. As you know, when you do just normal stress strain curves, the strain rate matters, the total strain matters. And so these are all important factors. That shallow grains lead to stress gradients that I'll show you in a while. And then there's a competition between different stress relaxation processes with different signatures. And one of the things that we're aiming to do is to actually develop more stress relaxation behavior damage accumulation maps. These are Ashby-like maps that show how the structures behave and how they change. So here's just a quick schematic that shows an illustration of a whisker and a tin film. Each of the grains has a different orientation. This is the structure of, this is a representation of a tin crystal. This is the unit cell. So it's a body-centered tetragonal structure, a squash structure. So you can see each of the grains has a different orientation, and they have different also mechanical behavior. So when you put these under you strain them, then the grains have different behaviors, different responses to the even just to the elastic component of the strain, and so these also enter in this as well. So you might be thinking, oh, these intermetallics, if they're causing this is just from room temperature growth. If these intermetallics grow and they're wedging up here in between the grain boundaries, or partially wetting the grain boundaries, maybe that's where the whiskers form near where these happen. Hay et al. Found that was not the case, that it imparts a more generalized compressive stress to the film, and so they form in places away from where the intermetallics are forming. What's interesting about anisotropic systems, very anisotropic systems, is that it depends, the actual response depends upon how you put the stress on and what the temperatures are. So this is a skeleton structure. These are calculations for different crystallographic textures. So this one is predominantly an 001 texture, 111, etc. And so given that the elastic anisotropy in these systems is really high, in this case, for example, an 001 texture, so this is ambient and this is strain energy, and elastic strain energy density plots. So this is just assuming that it's elastic. If this is with the intermetallics growing between them, where red are the hot spots where one would expect that the stresses would be higher, that the pattern here is very different from the kinds of patterns that you would see for thermal expansion differences. So this makes the problems a little more difficult to sort through, but I think we've made some progress in that. So it matters, if you're trying to mitigate this, and you don't want the whiskers to form. And sorry, I should have mentioned earlier that the problem is these tin whiskers form from electronic components. These tin films are on electronic components, and almost all electronic components have these tin films. And if these whiskers form, they can cause shorting between components. So if we were trying to design a texture for the ambient condition, the intermetallic growth picture, we would choose this one. However, if it's also exposed to thermal cycling, well, you would choose this one, which is about the worst for the ambient. So we really can't find special microstructural features, general microstructure features that would change the tin whisker risk. So here's an ion beam contrast image that shows grain orientation You can see here the darker ones are all grains all in the same orientation. So even when we're looking at something that's where we know the measure the crystallographic texture, there are pockets that have higher densities of certain orientations. And again, trying to figure out how one whisker out of 1,000 or 20,000 grains form has been challenging. So here are just some of the microstructures that one sees. This is a hillock. This is the original grain that popped up. Grain boundary migration took place. And this is the final position of the grain boundary. The shallow grain is underneath. So we have a lot of different features of the stress relaxation. Many of them just how the individual grains shape. The grains actually rotate. They can break up. Cracking, grain boundary migration, new grains can nucleate and slip bands. So we're focusing on dynamics and the microstructure. So there are 4 different conditions that we've explored: intermetallic growth, rapid thermal cycling, in situ SEM thermal cycling, I'll not be talking about today, and different microstructures, electrodeposited polycrystalline thin films. Most of the ones I've shown you so far are that way, and then some pseudo bicrystal thin films, so focusing on dynamics. So we know we can control the microstructures that form by changing the characteristics of the film. So this film has 2.1% copper in it. There are intermetallic particles that are pervasive through the film, and so this whisker grew out of the film with very little with little or no grain boundary migration. So you can suppress the grain boundary migration by pinning the grain boundaries. This is one with zero copper in it. So the grain boundaries were not pinned. And again, you can see this is the pattern over time. So we've done in situ experiments with this where the grain will grow out for a while, then the grain boundary migrates, and then it grows out again and the grain boundary migrates. And so these are quite dynamic changes. You can see here, this is the pattern this is where the triple junction was as a function of time from here down to here. And all of these, again, this is the curvature of the boundary on the free surface. And this is one in between. So you can see it grew up as a whisker over some amount of time. Again, this is the triple junction moving down. And so it's important to note that if this were just migrating due to curvature, that the shallow grain, due to curvature, actually the grain would actually shrink away to 0. And so the stress stabilizes this shallow grain and forces the grain boundary migration. Excuse me. So the way we've thought about this is a problem that is a trade-off between accretion of atoms at the bottom to relax the stress and grain boundary sliding. So this is a schematic of a cylindrical grain in a film. So imagine most of the grains in the film, look sort of like this, right? But this is just schematic of a cylindrical one. It's got a radius R, a height H, and the film thickness T. And if all of these are the same, there's a grain boundary sliding stress because remember, this grain is being constrained by having it's in a compressively stressed film, so it actually takes a force to push the grain out against this the sliding stress. So we did a simple calculation. So this is the accretion stress. So the stress down here pushing it up is pi r squared times that stress has to be greater than 2 pi r h, which is the area, the cylindrical area times the sliding friction. So it's a simple equation. And so for cylindrical grains where all these are constant, then we'd say that we come up with the prediction that the critical radius, there's a critical radius that relates the grain boundary sliding friction to the accretion stress, and it is proportional to the thickness. So this says that the grains have to actually be bigger than the average for this to happen. And there is a paper by Shafir, Rees, and Kaplan that, as just a throwaway comment, they said, oh, by the way, we had these hillocks forming. Hillocks, which are short whiskers, and they formed with the largest, only in the where the largest grains formed. So now let's move to how we describe the tin whisker formation. And so we have again this cylindrical grain, and we also have an oxide layer on the top surface. So not only does the accretion stress have to be greater than the grain boundary sliding stresses, then we also have the oxide. We have to actually be able to break the oxide. So that's the oxide fracture stress. And so we come up with a set of equations that describes what that trade-off should be. And here's one set of experiments we were doing in silver. And so this illustrates in silver what happens if we put even an organic film on the free surface. So this is a 50 nanometer thick film on silicon, and we heated it up and cooled it down. And the student did extensive microstructure analysis through here in EBSD. And unfortunately, that led to formation of an organic film on the surface. And what you're seeing on the free surface, these are AFM, is that the hillocks and whiskers formed outside of this region that we thoroughly characterized. So this actually is an illustration of the role of an oxide or a capping layer film. So this was a contamination layer. So let's transform this from the whisker growth from so we have a shallow grain. So instead of a cylindrical grain, this is a schematic of what a shallow grain would look like in the film, and a straight whisker growing normal to the film surface. So we have, again, it's compressive stress. The position here, like on the free surfaces, it has it's under tensile stress relative to these boundaries. And so there's a difference in vacancy concentration between here and here. This is under tensile stress. This is compressive stress. So there are more vacancies here than here. So the vacancies migrate here, the atoms move here, and this is how the whisker grows. And so we took this a little further, having sliding planes. So these are the sliding planes and accretion planes. And we have a model. We developed a model that looked at what that balance would have to be in order for whiskers to grow. And so we have a paper at ACTMAT that talks about what those transitions are. And so when the stresses are high enough, the accretion stresses, then we get out of plane growth and sliding out of grains. This is grain boundary sliding, limited cobal creep that causes whisker formation. And so if the film becomes tensile, what we have is actually these grains can become sources of atoms. And so we can see grains growing and shrinking. And I just recommend you going to the paper, and we have models of what the growth rate is as a function of these parameters. So I'm going to show you a few experiments where we have additional phenomena that are happening. This is CTE induced stresses in tin films on silicon. So it's heating and cooling. So we have the silicon substrates. And so in this case, we have the stresses due to intermetallic formation and CTE mismatch, and we have the effect of the oxides. We have all of these. And so one of the things that we see, and we're following these, and the graduate student follow these changes over multiple areas. So there are 9 regions in the system as a function of number of cycles, and was able to determine how the different microstructural changes happen. We couldn't do EBSD on these; the samples were too rough. As you see here that we have whisker formation here. We start to have more cracking. There's more whisker formation with 20 cycles, but what we're seeing is actually there's a decrease in diameter as the whisker grows. We see twinning, we see new whiskers growing, and we also see a phenomena where the whiskers actually pinch off. In this particular region, these grains actually sank. So in the whisker formation during rapid thermal cycling, what we see is that if we're thermally cycling it, we go to high temperatures, so the film's under compressive stress, low temperatures, it's under tensile stress because it's relaxed in between. So we see this grooving at the whisker root. We see the whisker diameter decreasing. We see striation rings on the whisker surface, sort of like tree rings, that each thermal cycling corresponds to one of these. And this is just showing what an ambient one looks like due to intermetallic growth. So what we found was that we actually get pinch off of the grains. And so you can see what the effects of compressive and tensile stresses are. And in the end, in this case, you see that there was grain body grooving on one side, but not on the other side. This is a fib cross-section of the whisker growing up. And you can see the holes that formed, which again were with each of these corresponds to one of the thermal cycles here and here, as the grain body groove penetrates and eventually the whiskers become so fragile that they break off. And here's a case where there's a sunken grain. So some grains only respond to the tensile stress component of it. And so this is at 2 cycles, 5 cycles, and 20 cycles. And you can see this grain actually became a source of atoms for stress relaxation in other places in the film. So we've done a lot of work on trying to classify what the different phenomena were. Surface cracking, grain body sliding were observed due to thermal cycling, but the extent was different with CTE mismatch. So we changed the thermal expansion coefficients by changing the substrates, and we looked at these in lots of different ways. We also looked at pseudo bicrystal films to try to see what's happening at the along these grain boundaries. So again, this is a tin thin film, but formed by melting and solidification. So it's about 20 or 30 microns thick. We thermally cycled these from -55 to 85 degrees C for 1,500 hours. And so what we saw was near the grain boundaries, we would form whiskers. We had regions that completely recrystallized. There was grain boundary sliding. And I'm not going to be able to share with you all the different components of this. But one of the things that we realized by moving to the bicrystal films that and initially for these grains, there is a single orientation all the way up to the grain boundary that because we're nucleating new grains, the dislocations must somehow be involved. And we think they're also involved in the polycrystalline thin films and columnar systems, because you can see that there won't be whiskers forming, and then all of a sudden at a critical point, that the whiskers will begin to form. So these were 4 different phenomena that we saw. No changes, sliding, nucleation of new grains, and then combinations of the two. And one of the key things that we found in doing fib cross sections here is that we could see that there was nucleation of new grains. So in this case, C is over here. So there's a change in orientation here. The top surface is tilting up, and as it tilts up, this tilting up corresponds to actually a change in orientation and it must be happening by accretion of dislocations in here. So we do EBSD here, and at other positions along the boundaries, this is the original boundary, is that we see the formation of a new grain boundary by the accumulation of those dislocations. And then once the boundary actually forms, then the whisker can begin to grow. It grows on both sides, not just tilting up. So we've done some extensive work. I'm not going to go into it, extensive work characterizing what those changes are as a function of number of cycles and when the nucleation happens, because most of our experiments earlier on were just a before and after thermal cycling. So hopefully this will be out soon, and it's fascinating work. It was really painstaking for Sung Ying Wang to do these experiments. So we've also done simulations that show this is where dislocations are accreting depending upon the misorientation. So we have some estimates of what the dislocation generation is near these free surfaces, and it depends on the loading direction, misorientation axis, and they're not everywhere. So here are just some calculations done in a paper we wrote, but seeing what the dislocation densities would be. But I'm not going to go into these details. We did some experiments on cantilevers. They're vibrating the cantilevers, and so this is where they're held. And so tin on silicon on copper, and you can see as a function of number of cycles, this illustrates the damage area. So here the strain varies linearly along a cantilever. So please take advantage of that wherever you can, because it means that the strain amplitude can be varied. So this is along the cantilever in a single experiment. So what we saw was tin whisker formation. We saw breakup of grains, and I'm not going to go into much detail. These instead of the original grains forming whiskers, we nucleated new whiskers along the grain boundaries, and these new whiskers could grow hundreds of microns in a very short time. And here are breakups of grains, and these have been seen in aluminum films and copper film and other films under different stress conditions. So we have number of cycle dependent, time dependent behavior, and we were able to basically go backward to make the link then to the Trinks and Volker paper to really begin to distribute, to determine the distribution of deformation mechanism. So hopefully someday we'll be able to develop these behavior maps. These are some Ashby maps on the right-hand side for different conditions. It takes a lot of careful experimentation, and I've been really very lucky and very I'm very grateful to all the people, and particularly the students with whom I've worked on this. And we've been supported in this by a number of different organizations, companies, NSF and all. So thank you very much. And I appreciate your being here today. So if there's time for any questions.
Thank you, Professor Handwerker, for that presentation. It was very informative. So anybody with questions, please either raise your hand or you can unmute yourself and ask your question.
Yeah, I have a question. So are you trying to form or trying to prevent these whiskers, and like what's the application implications?
So what I'm trying to do, and over the years, what I've tried to do is to try to prevent them from forming, because I work with computer circuit boards, and I work with the Department of Defense in particular that have a lot of critical microelectronic systems, and they do not want there to be short circuits. These tin whiskers can form short circuits and have formed short circuits. And so we want to prevent them. And basically what we found over the years is that because dislocations are involved in this and they can accumulate. We can't stop them from forming except by putting an even stronger capping layer on the surface. And that capping layer uses, it's a very strong polymer system that's put in. So I have a circuit board. I take the whole circuit board and I put it into into a vapor phase reactor with something called perylene, and it then coats all the surfaces. So we have to do something like coat the surface. It's called a conformal coating. You hope it's conformal. Conformal meaning it conforms to every free surface everywhere, because if it doesn't reach everywhere, then the whiskers will form where the stresses can be relaxed. So yeah, we want to stop them. It'd be fun if we could find a way to make them and harvest them, but I think there are other ways of making whiskers and nanowires. But thanks for the question.
Okay, thanks.
All right, anybody else? Oh, Principal.
Hi, this is a really interesting phenomenon, and particularly the whiskers are so narrow. I think there would be just an enormous surface energy penalty. So it's remarkable that these grow. Does surface energy play a significant role, or is just the incremental growth so favorable because of the forces involved?
So
I think it doesn't matter so much.
Yeah, that's a really interesting question. We've thought about that a bit. Let me go to the one of the earlier images. And actually, I think this one will do. I think the surfaces are actually pinned because there are grain boundary grooves in the oxide. So having the grain boundary grooves there in the oxide actually stabilizes the surfaces. And so I think that's one of the reasons why, yeah, surface energy doesn't play a significant role as far as I know. The other thing is that this happens in gold and silver, and there are conditions, where we can make all of these happen in different systems. So I think the surface energy is a small component, particularly if you're talking about thermal expansion mismatches, because you can generate really large stresses due to the thermal expansion mismatches between the tin film and silicon, or gold and silicon. So those, I think, have an even bigger role to play. For example, in making the grain boundaries of the small surface grains, the grains grow, and it's very much like the abnormal grain growth problem. Why was that migrating against its curvature? Well, in this particular case, they're migrating against the curvature. Surface energy effects would actually have them collapse to zero. So that's our analysis. If you have other suggestions, I'd love to hear them.
Not in particular, thanks. Very interesting phenomena here. So, thank you.
I have a quick question.
Please.
So how common do you think this effect is in other kinds of materials? Does it happen in a lot of materials, or do you think that tin is pretty unique?
So first of all, tin is not unique. Another system that does this is aluminum. And aluminum has a natural oxide layer on it, and it's been known to happen for many years in aluminum films. That is, among the earliest literature in this. So I think if you can make the capping layer thick enough, and you can end up suppressing it, but it also depends upon what stresses you impart to it. So with aluminum, you have to have it has to be the strains have to be imposed by the thermal expansion mismatch, and they have to be quite large. And you have to create it under conditions where you create the you create the strains, and you don't activate lots of other stress relaxation mechanisms. So if for example, in the tin films, if I heat them up to slightly higher temperatures, then the whiskers don't form. So you bring in other kinds of stress relaxation phenomena. They change as a function of temperature. But in aluminum is the classic case. I don't think anybody's tried in copper. We were working in silver films, and we certainly got hillocks to form in those films, which are short whiskers, where the height above the surface to diameter ratio is about 1:1. In gold, it's seen. I think it's the condition of having the film that's sort of 60% or more of its melting point, a tenacious oxide layer, and there aren't many other stress relaxation mechanisms operating. It makes tins such a great whisker former. Cadmium also forms whiskers. Zinc is another system that forms whiskers prolifically. And so in server systems, server farms, and this used to be for big computer mainframe system where you had to have big coolings systems attached. They would have raised floors, and they had to make sure that that they didn't use particular zinc films, because they would form whiskers, and then all the whiskers would break off and get sucked into the airflow and cause the computers to fail. So, yeah, I think you just have to choose your metal and decide, what regime you want to, what temperature regime you have to go into, and strain regime to force this to happen.
Thank you.
Sure.
All right. Is there any other questions? Any more questions from anyone else? Okay. If not, I'd like to thank Professor Carol Handwerker again for her interesting seminar. Thank you so much. And thank you everyone for attending the seminar today. And hopefully we will see you all next week. So thank you very much. Thank you. Thank you, everyone.
Thanks everybody for coming. I really appreciate it. Take care.
Yes, thanks very much, Carol. So let me stop the recording and the YouTube. Great. I'm going to stop the YouTube. I've never tried to do this. I've always just stopped the Zoom and the YouTube stops.